In this video, I'm going to show the image of why we need to transmit the encoded data to the SerDes interface. Before talking about why we must transmit the encoded data, let's start to review a few impairments items in the SerDes. In the while timing video, we've known the phase alignment of the sampling clock was accomplished in a cross correction loop. For example, if the clock phase is late, then the phase detector PD output will send an up control to adjust the clock phase to be earlier. On the other hand, if the clock phase is early, then the PD output will send a down control to adjust the clock phase to be later. Finally, both PD should guide the phase of the sampling clock to be in the middle of the data I and have the most I high and I width margin, according to the criterion of the phase adjustment. Do you see any issue here? Can you think about the random data images for 5 seconds? Good. The phase comparison of the PD came from the data transition 1 to 0 or 0 to 1. But the random data without any encoding could have a very long run, consecutive 1 or 0 without transition. Ideally, the PD should provide no update information if there is no data transition and keep the clock in the Tristate without moving the phase. Unfortunately, the charge pump of the CDR would have the current mismatch, such that the VCO phase or frequency will still drift earlier or later during the open loop state, even if up equals down. Furthermore, even though we could have a perfect charge pump without any mismatch, the power supply should not be perfect without any supply noise or ripple. Therefore, the VCO phase will still be drifting due to the supply impairments or the VCO intrinsic jitter during the open loop operation, which came from no data transition. At this point, you should have a better image of the encoding or decoding of the low random data should make data transition more often in a bounded way and help the clock recovery operation in a more robust way. The phase alignment in the time domain helps reduce the bit error. Do you see any benefit of the encoded data that will improve the bit error in the voltage domain? Think about the image of the AC coupled C-link in 5 seconds. Bingo! As we will discuss in the why DC coupling or AC coupling video, the AC coupling may cause a sweet attenuation if there is a very long run or very low frequencies of transmitted random data with a relative small DC block capacitor or large cutoff frequency and high pass filter. And this phenomena is called a DC over baseline wandering. Without any encoding, there's no way to make sure the DC block capacitor was always really big enough to make sure the cutoff frequency to be low enough compared to the lowest frequency content of the input raw data. And then you must see the DC wandering from the raw data. Then the I high will be reduced due to the DC wandering, and then the bit error is increased. So you must see a better image of the encoding or decoding of the raw random data should bound the data transition and the lowest frequency of the data content, such that the minimum capacitor value could be bounded well in any protocol standard to mitigate the I high degradation. In addition to the bounded data transition, what else would be the requirement of the encoded data to avoid the DC boundary? Correct. The DC bands, which means that the number of zeros transmitted must be the same as the number of ones transmitted through AC coupling capacitor to remove the DC offset of the large 1 or large 0 to a different switch level, which would reduce the I high and increase the bit rate. Since the encoded data with the limited long run and DC bands are so important to provide the best performance in a SerDes. Let's talk about a few line calls here. The first line call is the Manchester call, which is an extreme case to always have a transition of each bit period, and it must be a DC band since it does not have any DC component at all. The data information is remade as follows. From the waveform image, it should be easy for you to tell a low to high transition represents a large 0, and a high to low transition represents a large 1. Is this Manchester encoding difficult to generate by looking at the clock and data waveform here? Can you please look at the clock, NRZ, and Manchester data image one more time? Correct. It's very easy to generate the Manchester data by XOR, inclusive of the NRZ data and the clock. So this Manchester data will not only help the CDR much easy synchronization without phase or frequency drifting, but also provide a minimal DC block capacitor size in an AC coupling C-link. Do you see any issue with it? Think about mode transition in a time domain image can imply the bandwidth in the frequency domain image for 5 seconds. Perfect. Intuitively, mode transition implies more high frequency content, and the bandwidth will be wider. Therefore, the bandwidth requirements of the SerDes transmitted to the Manchester data at the interface front end will be almost twice the bandwidth requirements of the NRZ data. That's why Manchester data was used at a very low data rate, but not a high-speed C-link anymore. To be straightforward, no one can afford 100 gigabit per second data throughput, but requires running at 200 gigabit per second with more than twice the power and much high design challenges in the link. So let's go through other line calls. The second line call is quite popular and useful in most SerDes protocols, such as the DisplayPort RBR up to HBR3 and PCIe Gen 1, Gen 2, which is called the AB10B call. The AB10B encoding maps 8 bits words to 10 bits symbol, and it's a PRBS7 approximation to provide both the DC balance and bounded disparity in the data transition. Therefore, the number difference between the large 1 and 0 in a data stream is only 2 during at least 20 bits. In addition, there are not over 5 ones or zeros in a long run, which should not have a long run and result in a very high frequency of data low frequency content. Lastly, a simple AB10 mapping image is shown here, and you could review it if that match your expectations. Again, the AB10 encoded data may meet both DC bands and at least one transition in 5 bits without adding the transition all the time in every bit in the Manchester data. Do you still see any issue in terms of the bandwidth image? Can you think about the images of 8 bits in and 10 bits out one more time for 5 seconds? Bingo! Thanks to AB10 bits DC bands and frequent transition, the circuit's performance could be enhanced, and the whole SerDes impairments could be relaxed, but the bandwidth overhead is 25%, and the throughput is waste due to the encoding. For 1 gigabit per second raw data transmission with AB10B encoding. The 10 bits data was finally transmitted one at the SerDes front-end interface. So your transmitting data rate in the SerDes design should be 1.25 gigabit per second instead of the 1 gigabit per second raw data. Apparently, the overhead at the 1 gigabit per second or 5 gigabit per second was probably okay in terms of 25% more power and design overhead. But for 10 gigabit per second and above, the power and design overhead will be an issue. Therefore, we may want to look for other line costs. So, I'm not surprised. Another 64-66-bit encoding was used in other high-speed or high data rate standards like 10G base KR or 40G base KR. The encoding bandwidth overhead can be reduced as little as around 3%. Other bandwidth efficient encoding like the 128-bit, 130-bit used in the PCIe Gen 3 to Gen 5, since the 64-66-bit maps 64 bits to 66 symbols, which is a PRBA31 approximation. The 10G data transmission would require the Sealink to operate at 10.3125 gigabit per second. Again, do you see any power or design big difference between the raw data or 64-bit, 66-bit encoding data from the data rate difference? Of course not, but there is no free lunch. Do you see any other trade-off images? Bingo! Since the encoded data is mapped to 66-bit symbol, the maximum long run consecutive 1 or zeros would be 66 bits, not 5 bits, in the AB10-bit one. Therefore, the clock data recovery CDR must tolerate a 66-bit long run or even 80 bits run length, a stress test in the protocol standards. Hopefully, this will not be an issue for CDR, since most industrial CDR designs have been confirmed such 80 bits run length is reasonable to achieve. But the jitter performance of the CDR will still degrade steadily from the AB10-bit data to the 64-bit, 66-bit. If there's a possibility to have a 66-bit run length, what else could be the issue? Think about the DC bands for 5 seconds. Correct, technically, at such a long run length, the DC is not balanced if you only check the short bit stream, like 10 bits or 20 bits. So, the voltage or I high would degrade from AB10-bit data to the 64-bit CTC data. Hopefully, we still can achieve the DC bands over the long run statistically by the scrambling tricks, and the I high might not degrade a little. Here is a summarized image of why we need to transmit the encoded data to the SerDes interface. To have the clock data recovery CDR work robustly, we must provide enough data transition. Furthermore, to avoid the DC wandering or offset in an AC coupling Sealink, we must provide a bounded disparity in the transition and DC balance data. The simplest encoding data is the Manchester data, which does not have any DC content and has a guaranteed transition in each bit. But the bandwidth overhead was too much and cost almost more than twice the power and design overhead. So the Manchester core was only used at the raw data rate. Hopefully, the AB10-bit will still provide a DC balance and a maximum 5 bits run length, which is only 25% bandwidth overhead. Again, the AB10-bit data was quite popular since it boosts the SerDes performance and reduces the design complexity a lot. Unfortunately, when the speed goes around or beyond 10 gigabit per second, the AB10-bit 25% bandwidth overhead was still too much to have the same benefit at the data rate such that the AB10 bit only fits well at the medium data rate. Other more bandwidth efficient code than the 64-bit 60-bit would only have 3% bandwidth overhead, which is very attractive at a high data rate beyond 10 gigabit per second. Of course, the run length would be 66 bits in the 64-bit 60-bit, and the CDR must tolerate 80 bits run length for a stress test in the protocol. Also, the DC is not balanced in a short run length to be specific over the long length statistically by scrambling. The 64-60-bit data is still DC balanced, and both the I width and I height might still degrade slightly compared to the AB10-bit data transmitted at the same data rate at the interface. Thanks for watching. Before you go, if you are benefiting from those circuit images, I would love to hear your feedback and please share your comments down below. Lastly, please share the video link with the people who may be benefiting from it.